Alrighty. Well, why don't we go ahead and get this train rolling? Okay, so today, what do we want to talk about today? I know it's been a while since I've done one of these things, so in the past few ones, what I've been really trying to do is start looking at things in higher dimensions. One-dimensional physics is great and all, but it's very limited. So I want to really start talking about things in higher dimensions. So started talking about things like angular momentum and dealing with vectors to do our physics. But what we haven't talked about for higher dimensions are work and energy. And these, of course, are very important things to have in our arsenal to do physics. So it'd be great to be able to generalize these ideas to higher dimensions. So to do that, though, since we are starting to work with vectors and things in higher dimensions, we have to be able to generalize our machinery, so our mathematics, to be able to do those calculations in higher dimensions. So we're going to just start looking at vector calculus. We're not going to go super in-depth on it, at least today, but we're going to start dipping our toes into some vector calculus. It's not anything to be afraid of. It's just sort of, like I said, we're taking what we already know and trying to apply it in more dimensions. And so once we have that under our belt, we'll be able to really start digging into work and energy to be able to prove some very interesting stuff. And hopefully towards the end of this, we'll make some very interesting connections between things that seem like they shouldn't really be connected at all. Okay, so with all that said, let's start talking about all of this stuff. So in one dimension, whoops. So when I had things in one dimension, okay, so I see a question. When I say higher dimensions, how high do I mean? So in principle, we could be talking about any number of dimensions, but really been trying to focus in on 3 dimensions because obviously that's sort of the most physical case that we care about. So at least for the time being, and when we're dealing with classical physics, we're going to be mostly dealing with 3 dimensions. Okay, so when we did stuff in 1 dimension, what did we have? So we had things like we had our position, which could be a function of time, velocity, function of time, acceleration, all these things which were functions of time. And, of course, we also had things like Newton's second law, which is F equals ma, which, of course, all of this stuff all of this can be functions of time. But we also saw in the case of, say, I have some mass on a spring, whose displacement I might describe by x. So I also saw that force could be a function of position. In this case, it was minus kx. Now, in 3 dimensions, or in any number of dimensions, I guess, since we had the question, a lot of this story was the same, except now we're talking about vectors, right? Where vectors, of course, are things with not only a size, but also a direction. So, yeah, and so, again, we can just draw sort of parallels to these sort of things, and forces are now going to be vectors. And if I draw a similar parallel here, where now, I can have my system be anywhere in this 3-dimensional space, right? This is now described by an x vector. I could have some force vector, which is in principle a function of position. Okay, so in this one-dimensional case, when we talked about work, we talked about it as the integral from x1 to x2 dx f of x. So what we really want to be able to do is draw our three-dimensional analogy to this. And so to do that, we should try to get sort of a concept of what this is telling us. We sort of did that before, but let's just sort of reiterate that. So what this is saying is that, okay, so in my one-dimensional system that I'm looking at, say my box is moving some distance d, right? Or I guess we'll say it starts at some x1 and moves to some x2. And we'll say that there's some force acting on it. It could be acting this direction, it could be acting this direction, whatever it may be, but I have some force, which could be a function of the position, acting on this box. Now, all this is saying is that as this box moves from point x1 to x2, I just add up the entire amount of force that I exert on this object as it moves from x1 to x2. That's all this is saying. So we might think that if I now move on to a three-dimensional system, so say I have some axes, so call this x, call this y, call this z, and now I have some mass, it could be a box, it could be a ball, whatever it is, and it moves along some path, which I'll call p. So again, we might say, okay, well, this is probably just going to be the total sum of the force exerted along this path. But we have to be a little bit careful because in this case, we only really had one direction that the force could point, whereas here, it can point in any number of directions. So why don't we say that, okay, let's, instead of trying to make things too complicated, let's just break this down into 3 one-dimensional problems. So I might say, okay, well, in the x direction, so it starts from some point here, and then it moves over to some point here. In the y direction, it starts here, and then maybe moves to here. And then in the z direction, which it may move some direction here. So I tried to draw these a little bit creatively so that they're all independent, but hopefully you get the idea. That's a great question. Are the forces considered conservative? And we will get to that. We will get to that in a second. Right now, we are not assuming anything about the forces. They can be completely general. But that's something that I want to get to later on. Okay, so let's just say that the total work, then, is the work in each one of these directions. So I might say that the work done is equal to the work in the x direction, plus the work done in the y direction, plus the work done in the z direction. Now, since my force is a vector, I know that it has some piece in the x direction, some piece in the y direction, some piece in the z direction. So I might write that as my force is equal to F sub x, x hat, plus F sub y, y hat, plus F sub z, z hat. So now all I have to do is, well, I pair these up, right? So I know my expression for one-dimensional work, so I'll just pair each of these up and say that my work done is equal to the integral from x1 to x2 dx, the force in the x direction, And keep in mind that this could be a function of x, y, and z, but we're only integrating with respect to x. So it's that plus the same thing in the y direction, y2, dy, f sub y, x, y, z, plus z1 to z2, f, z, x, y, z. Okay. Now, one other thing that I'm going to introduce is a differential position vector. So instead of saying, okay, I have some position vector which points from my origin to some point on here, I want to look at the vector which takes a change in some, change colors here, which measures the change between 2 points which are very close together along this line. So I'll call this dx, and basically if I zoom in really close, I'll draw in a little zoomed in picture. So I have some curve here, and what this is really going to look like is it's going to be some vector which is pointing, which is tangent to the line that I care about, right? So it's the change in this small tiny little region. Now, taking that into account, where I can define this as the tiny amount of change in the x direction, tiny amount of change in the y direction, tiny amount of change in the z direction. Right, so this is just some vector which describes how much it's changing at any given point, how much the path is changing at any given point. Now, keeping this in mind, this comparing, well, if I match up these two things and look at this expression, it looks very much like a dot product, what we would expect from a dot product. So I might be able to write something like work is equal to the integral over some path times this dot product, where in principle this f could be is some function of the position. And so this is actually what we're going to work with. No pun intended. But so yeah, where p just tells us what the bounds on these integrals are, and that's going to tell us, or that's going to be determined by whatever path we decide to take through space. As we'll see soon, in some cases that path is going to matter, in other cases it won't. And actually most of the time, the cases that we look at, it ends up not mattering. Okay. So let's go ahead and look at an example of this. And particularly look at this case of what happens to work when I consider different paths through space. Okay, so let's consider a force which looks like just our ball on a spring, or a mass on a spring force, but in 3 dimensions. So what's this going to look like? So this is going to look something like I have my axes here, and I'm going to have some mass, which I'll draw in blue, described by a position vector, which I'll call x, like that. And the force is just going to be acting in the opposite direction of that position vector. And it's always going to be trying to pull it directly towards our origin. Okay, so let's try to find the work done by this force along some different paths. So the first path that I want to look at is, okay, we'll start, let me draw this a bit differently. So I will go ahead and draw this bigger. Actually, I'll take these axes out farther as well. So X, Y, and Z. Okay, and so let's look at the path, or let's essentially think about taking the mass along a specific path that we care about. So let's just go ahead and start with a path that starts at the or on the negative x-axis. So we'll say it starts at -1 on the negative x-axis. And then we'll move it to a point in the YZ plane. So we'll move it to 1, 1 in the YZ plane. So it's going to come up to here. And then we'll bring it back down to the positive x-axis. So we'll move it back down to 1 on the positive x-axis here. So it comes back down to here. Okay. Question, is that a Newtonian force? I'm not exactly sure what you mean by is that a Newtonian force. Do you mean that I can write this as MA? If that's the case, then yes. That's this is typically the equation that we solve to get the back and forth motion of a spring on a mass. But okay. So we'll say that the initial point that it starts at, we'll call it P1, is equal to minus x hat. And then it goes to some point P2, which is going to be y hat plus z hat, which then goes to P3, which is just going to be x hat again. Okay, so now what we can do is we can consider the work as just being the sum of the work done along this first path here. I'll use red. And then plus the sum of the work done along this second path. So I'll call this P12, call this P23. Okay, so then I can write the work as being the work 1, 2 plus work 2, 3. So the work done along P12 plus the work done along P23. Well, this is pretty simple to do because we just look at, we'll say 1, 2, P12 dx vector dot f, which is going to be equal to the integral from, well, so we'll start with our x integral, dx f sub x, but we know that f sub x is just going to be equal to minus kx, because that's the force in the x direction. And we start from -1 and we go to 0. Plus the integral dy, which again is going to be minus k times y. We start at 0 and then go to 1, plus integral 0 to 1 dz minus kz. Hopefully you can see everything there. I'll move this last one down a bit. Plus integral from 0 to 1 dz minus kz. Okay, so now we just do these integrals, and we find work 1, 2 is equal to, well, this first, I can pull out a whole factor of minus k from all three of these. This first one is going to be x squared. The integral is going to be x squared over 2, so x squared over 2 evaluated from -1 to 0, plus y squared over 2 evaluated from 0 to 1, plus z squared over 2 evaluated from 0 to 1. I do believe that that is correct. Okay, and so now I just go ahead and plug everything in, and you'll see that this piece actually ends up canceling one of these, and I get something which looks like minus k over 2, I believe. Okay, hopefully that makes sense. If there's any questions, feel free to let me know. I'm going to take a quick pause here before we do the next path to hopefully try to catch up on some questions and let that sink in a little bit. So just like a centrifugal force, basically like gravity. So it's similar to gravity in that it's a purely radial force. Now, if it's going around in a circle, then you can call it a centripetal force if you'd like. But it's not quite a centrifugal force in the way that it shows up because of a non-inertial frame. I hope I'm answering that question correctly. Or I hope I'm understanding your question correctly there. Okay. Okay, so I'm not seeing any more questions showing up. So let's just go ahead and do the second part of this path, which is going to be the work done from point 2 to point 3, which is going to be starting with the x integral, which again is just minus kx, because that is the force in the x direction. And this time this goes from 0 to 1. And what we'll find is that a lot of this story is very similar. I'll go kind of quick because we just saw the calculation, and basically we're just putting different bounds on this integral, minus kz. And when we do this, when we evaluate all of this, what we find is actually that we get something which looks like k over 2. If you'd like me to go through this in more detail, let me know. But for right now, hopefully it's easy to follow that this is just k over 2. So when I add up the total amount of work, this is going to be work 1, 2 plus work 2, 3, which is minus k over 2 plus k over 2, which is just 0. So along this particular path, we found that at the end of the day, we've done 0 work. Basically meaning that as we go along this first part of the path, in some sense, the force is, some parts of the force is working with us, and some parts of the force is working against us. And then we just sort of flip that sign when we go along the second path. Okay, so let's go ahead and look at a different path. I mean, things seem to depend on paths in this story, so let's talk about a different path. So in this second path, let's take a bit more direct route. So I'll go ahead and look at x, y, z, and I'll start at the same point, and I'll end at the same point. But how about instead of going in a roundabout way, we just go directly from the first point to this, the last point. And so I'll just call this path P. Well, in this case, the work is just given by the work is equal to the integral dx minus kx, because that's our force. And in this case, we're going from -1 to 1. But in the other cases, in the y direction, I'm staying at 0 the entire time. I never leave y equals 0. And I also never leave z equals 0. So it's easy to see that these two are automatically just going to give me 0 when I do that. And so I only care about the work done in the x direction. Basically, we've reduced this to a one-dimensional problem. And in this case, I get something like minus k over 2 times x. Well, I get 1 squared minus minus 1 squared, which again gives me 0. So the same answer I had before. Okay, just to make sure we're not crazy about this, let's consider one final case, and also talk about something interesting while we're doing so. So in this case, I'm just going to draw the xy plane. We're going to assume that it always stays in the xy plane, never moves in z. So again, we'll start and end at the same point. Here and here. But now let's take a circular path. If I can draw a circle, hopefully. So this is going to be our path now. Say this is x and this is y. So we take a semicircular path from x equals minus 1 to x equals 1 in the xy plane. Now we could do this in these xy coordinates, but that actually turns out to be very inconvenient. And what's actually much simpler to consider is instead of saying, again, I'll just redraw the xy plane here. Instead of saying I have some point here in the xy plane, which is parameterized by some vector, which is some ax hat plus by hat, what actually ends up being much simpler for this particular case is to just say that it's given by some distance, so I'll call that r, just from the origin to the point, and then some angle from the x-axis, which I'll call phi. So when I draw all this out, what we'll find is if I draw lines of constant r, I get these circles coming out. Now if I draw lines of constant phi, I get something which looks like this. And although the things might look weird, we see that r and phi are still perpendicular to each other. So in this case of x and y were always perpendicular to each other. Here, r and phi are still always perpendicular to each other. But, so the force that I'm considering in this case is minus kx, which is given by the position vector in this three-dimensional space. But what you'll notice is that this position vector, so I have my position vector here, and so previously I would say, okay, here I have some x hat and y hat. Whereas now I'm going to change things a bit, and I'm going to talk about things as things in the radial direction, which I'll parameterize by r hat, pointing outwards from the origin. And then I'm going to parameterize the other piece by phi hat, which just points along this angle. So you can see that as I rotate this vector, so maybe I rotate it to here, I'll have my r hat direction and my phi hat direction now point in different they may point in different directions, but r hat always points directly outwards from the origin, and phi hat always points perpendicular to that. But this is my x vector, right? This is the distance vector from the origin outwards. So this x vector is always going to be in this radial direction. So this phi hat won't ever actually show up in a position vector like this. Now maybe if I have some velocity vector which is pointed in this direction, then phi hat might show up. But when I'm talking about position vectors, I only ever care about r hat. And in this case, z hat comes along for the ride as well, because remember, we're working with 3 dimensions, and we've only really dealt with things in 2 dimensions in this picture. So I'm going to call this, give this the name of r hat plus z hat. So phi doesn't show up in this picture. Okay, so now I'm going to be a little bit sloppy with my argument. I'm not going to be super rigorous because the details can get kind of complicated. But what you'll see is that since I'm taking a circular arc, this distance here, so the distance I'm at in the radial direction throughout this entire path is never going to change. Right? And so just like in the last example, where nothing ever changed in the y and z directions, I shouldn't expect any contribution from either r or z. Z because we're staying in the xy plane the entire time. But so I'm changing only in the phi direction, phi hat direction, but my force never depends on the phi hat direction. So when I do something like dx dot f, this is only going to give me something like drfr plus dzfz in this particular case. But like I said, these two never change, and so hopefully it's easy to see that the work will again end up being 0. Okay, so we've now looked at 3 different paths, all starting and ending at the same point. And we've always gotten the same final answer for the work done for any path, for all 3 of the paths, not necessarily any path. We haven't shown necessarily that it's independent of the path yet. So this seems to be sort of hinting at something fundamental. But maybe it's just the particular force we're looking at. Maybe this isn't always the case. So to investigate, let's look at a different force. Instead, let's look at friction. So if I have a friction, force of friction, I can write that as a vector. So I know its magnitude is going to be the coefficient of friction times the normal force. But what about its direction? Well, we know that the force of friction is always going to oppose motion. So we can write this as being directed in the minus v hat direction, where this is our unit velocity vector. So just the vector of length 1 that just points in the direction of the velocity of the particle that is traveling, or whatever is experiencing the friction. And the minus sign just saying that it's going to end up pointing in the opposite direction that we're moving. Exactly what we would expect of friction. Okay, so let's keep things simple. And let's just keep things restricted to the xy plane. No need to involve z in all of this. So let's look at a couple of different paths. So the first path that we'll consider, we'll say we start at the origin. And now we'll travel along the x-axis 2, x equals 1. So I'll call this point 1 equals 1, 0. And then we'll go straight up to y equals 1. So I'll call this point 2 equals 1, 1. I'll keep my colors consistent. P2 equals 1, 1. And now I'll go back along the at fixed value of y until I hit the y-axis, at which point I'll call this P3 equals 0, 1. And then I'll just return down to the origin. Okay, and I'll just call this P0, and this is 0, 0. Okay, so like before, we can just consider the work done along each path. So here, since we're only moving in one direction, in each of these pieces of the path are all the same length, this is going to essentially end up looking like just 4 pieces, or 4 times one of the sides. So I can show it explicitly. So for example, if I go along the first path, I'm only ever going to get something in the x direction. So in this case, I'm moving in the x direction, and so my force is going to be this guy in the x direction. Now, for P1 to P2, I only get something in the y direction, and again, I'm moving in the positive y direction. And so I get something like this, minus opposing the motion in the y direction. Okay, and then I get something like I go from 1 to 0 in the x direction, but now I'm moving in the negative x direction, so my force actually flips sign. So this is going to be positive mu n. And then I get something similar for the last path, dy minus, or again plus, because I'm going in the negative y direction, and so the force is directed in the positive y direction. And so what we find is that this is just 4 times just one of these integrals. I can call what I put in here whatever I really want. And so taking the integral, assuming nothing changes in the x, so assuming that the coefficient of friction and the normal force are constant in x, this is just going to give me something like minus 4 mu sub k n. Okay, now let's again consider a similar thing, but a different path. And this time we'll again consider a more direct path. So x, again we'll keep the start and end point the same, so at P0, but in this case, let's just go out to P1, out to x equals 1, and then just turn around and go right back. So hopefully it makes sense that the same argument as up here is allowed. And so we get something which now looks like minus 2 mu k n. 2 because we only have 2 legs to our path, whereas 4 we had 4 here because we had 4 legs to our path. So in this case we see that the work does depend on the path. So what gives? When does it depend on the path? When doesn't it depend on the path? So to answer this question, we'll dive back into the one-dimensional case again, and then we'll try to generalize that story to the three-dimensional case, and this is where this vector calculus is going to start to come into play. But before I jump into that, I want to take a quick break, see if people have some questions they'd like to drop into the chat, and give some time to sort of absorb this information. So I know this has been a lot of just sort of math and formalism, but I promise towards the end we'll start getting into some very, very neat results. Okay. Okay, so I'm not seeing anything show up, so hopefully this is at least somewhat making sense. So, to sort of answer this question of when work depends on the path versus when work doesn't depend on the path, let's think back to just our general ideas of calculus, and in fact the fundamental theorem of calculus, which tells me that if I have some function, so if I have some function f of x, which I can write df dx. So I can write this function as a derivative. The f doesn't have anything to do with force necessarily in this case. This is just a general function. And again, remember, we're back in the one-dimensional case. So we only have one coordinate. This tells me that if I now take an integral f of x from a to b, then this, of course, I can rewrite as df dx, which, when I do this out, I just get something simple like this, right? Just big F evaluated at B minus big F evaluated at A. So now, and so all this is saying is I have, I go along this point, or this number line, and I add up the value of f at each one of these points, and that gives me the final result. But now, let's say, instead of going straight from A to B, I make a little detour, and I first go to C. C could be out here, C could be in here, wherever, but let's say I go, I make a stop at a different point. So, okay, in that case, well, why don't I just split this into two different paths, just like we did before? So the first one, I'll go from A to C, and then the second one, I'll go from C to B. And so this story is very similar to what we saw before. So we just split it up into the two pieces, and just by applying what we did up here, we can write this as f of C minus f of A plus f of B minus f of C. And what you see is that these two pieces cancel, and I'm left with the exact same thing as I had before. And so obviously this generalizes to any number of stopping points that I make, but the intermediate pieces always drop out. They always cancel in this way. So what we learn from this is that if I can write my function as a derivative, it's only going to depend on the endpoints. But this is the one-dimensional case, and we care about the three-dimensional case. So I have that my work is equal to integral dx times the, I'll say x1 to x2, times the piece of the force in the x direction, y1 to y2, dy fy, plus z1, z2, dz fz. So it looks like if I can write something like this, I don't know, if I'll give it a name. For right now, I'll call it v. dx fy equals dv dy fz equals dv dz. So it looks like if I do this, if I can do this, if I'm allowed to do this, then this will all work out and the work won't depend on anything but the endpoints, right? Just like up here. These are just three one-dimensional integrals, and so the story should be the same. But this is a little bit tricky because now we're working in 3 dimensions, which means that I can have non-trivial dependencies on, say, the x and y or x and z coordinates in here, in the or y and z coordinates there, the x and z here, and the x and y here. In which case, how exactly do I take these derivatives? So, the way to go about this is we look at what we're integrating instead of what we're differentiating. And what we see is that each one of these integrals completely ignores everything in the coordinates that we're not integrating over. Right, so this integral couldn't care less about the y and the z. This one doesn't care about x and z, and this one doesn't care about x and y. So, if I can define some derivative that does the same thing, so if I can write f as some derivative that only sees the x, some fy is some derivative that only sees y, and fz is the derivative that only sees z, then this should all be fine. This should all work out, because it's essentially, in that case, only a one-dimensional problem. And so the way we do that is with something known as a partial derivative. And the idea is a partial derivative of some function is, instead of having these lowercase d's, I just sort of upgrade them to some curly, these curly d's, in which case I can define this as exactly what I said. So the same way as a regular derivative, but now this v could have some dependence on other coordinates, but we're just going to ignore that in this particular derivative. So I can write that as this. Right, so exactly the same definition of the derivative, except now we have these extra coordinates, which are essentially just going along for the ride. So now we see that if I can write my force as some, and I'm going to use a little bit of a different notation here, minus du dx x hat minus du dy y hat minus du dz z hat, then all of this story should work out, and the work should only depend on the endpoints of the function. Right? Okay, so this is great. The reason why I defined it in this way should hopefully become clear soon. Basically, all I've said is that v is minus u. Okay, so now before moving on, I'm going to introduce a little bit of a more compact notation, and also note that u here is a function of x, y, and z in general. Okay, so now I'm going to introduce a little bit of notation, because this notation here it's very cumbersome to use. It's kind of hard to carry all of these different components around separately. So what we typically do is we define this object called del, or I think the technical name for it is nabla, but typically you'll see it referred to as del or as a vector derivative, and it's given by this little upside down triangle. And this is just this vector partial derivative, where I take the derivative along each component in that direction. Now, just like writing d by dx, it doesn't really make a whole lot of sense on its own, and really only makes sense if I'm actually acting on some function of x. So, more formally, this is known as some linear operator. Just like our regular run-of-the-mill calculus one-dimensional calculus derivatives were linear operators, this is also a linear operator, just meaning it acts on something to give me something else. Okay, so writing this in the compact notation, I can write that the work only depends on the endpoints of the path if my force, I'll write this as force, which could be a function of position, is given by some minus del u. The minus sign is sort of a convention, and we'll see why this comes in handy very soon. Okay, so hopefully this is all making sense. Again, feel free to just drop any questions you might have in the chat, and I should get to them. But okay, so what is this function u? What is this? This would be great to know. Okay, so if we take the integral, the indefinite integral, so we want to look at something like dx dot f without endpoints. So we're not going to look at a path. We just want to integrate this. Well, this is going to be equal to minus integral dx du dx minus integral dy du dy minus integral dz du dz. And so, as we might imagine, this, at the end of the day, just like if I integrate out, so I'll write this in the more compact notation. So this is minus dx dot del u. So just like before, whenever I take a one-dimensional integral of some function, which is a which can be written as a derivative, and I get the function plus some constant, could imagine that this is also going to be equal to some my minus u of x, and I'll just write it as minus c here. So what we see is that my minus u of x is equal to f dx dot f, and I'll absorb the c into this integral for the time being, which tells me that minus, if I have some change in u, this is going to be equal to this integral along the path between the endpoints of u, right? So this change in u is going to be something like u x2 minus u x1, but this is just equal to the work. And from the one-dimensional case, we know that work is going to be minus the change in potential energy, so we can immediately identify U is the potential energy. Excellent question. What is U? U is the potential energy. U up to this point has been just some function. We know we can write f as the gradient or the vector derivative of u, where up to this point we were kind of not talking about an interpretation of u, just calling it a general function, so that the work is defined as only depending on the endpoints of the path that we take. So that was u, and now we just identified u with the potential energy. Okay, so this is excellent. So let's get an idea of what one of these, how we might do this calculation. Well, we can write again, I'll just write it in this way, integral dx dot f. So let's take the force that we were looking at before, which is this restorative force, minus kx, this Hooke's law. Well, in this case, I have something which looks like minus k, integral dx times x, plus integral dy times y, plus the integral dz times z. When I take all these integrals, I get something like minus k over 2 times x squared plus y squared plus z squared. But x squared plus y squared plus z squared is just the magnitude of the position vector. So I can write this as minus 1/2 k magnitude x squared. Oh, and of course, must not forget the all-important integration constant. And actually, in this case, I want to make it a negative. Just, it's a constant. I can call it positive or negative all I want. So I'll just call it negative. In which case, the potential energy of Hooke's law, corresponding to Hooke's law, which in fancy terms we can call a harmonic oscillator, is just equal to minus 1/2 k x squared, or plus, sorry, because we had a negative over here, it should be plus c, which is just some constant we can fix at our convenience. Okay, this is very cool. This is a very cool result, and this is actually a result that is used very often in physics, that the potential energy of a harmonic oscillator is 1/2 k x squared. Okay, well let's just go ahead and try another example. Look at another example of this. So let's look at, if you've seen some of my previous streams, one of them we looked at gravity, where we were able to derive the general form of the gravitational force just by looking at angular momentum laws and Kepler's laws, which using just those things, we were able to get it down to something which looks like minus some number, some constant, or some collection of constants, divided by the magnitude of the position that we are away. So I'll just go ahead and draw this out. I have some gravitating body here, and some second gravitating body here. And this is going to be my position vector. And of course its direction is given by x hat. So the force is just felt this way, and it's this inverse distance squared relation. Okay. So again, let's go ahead and look at a different coordinate system, one which is more suited for this particular calculation. And what we'll use is, it's known as spherical coordinates. So to look at these, what I can say is that I have some point in space, and this is given by the distance from the origin, the angle from, let's call this the x-axis, y-axis, and z-axis, which I'll call phi, the angle from the x-axis, which I'll call phi, and then the angle from the z-axis, which I'll call theta. And this distance I'll call r. Okay, so in this case, this all gets a little bit messy pretty quick when we're using spherical coordinates. It comes in handy, but in this particular case, we can see that it's only ever going to depend on our position vector, which means that we only ever care about what's happening in the r direction. So this actually ends up simplifying quite a bit as minus alpha over r squared, where r is just this distance, in the r hat direction, so that's this radial direction here, and nothing else, because it doesn't depend on anything other than the position that we are from the origin, or the distance that we are from the origin, and the direction of that distance vector. Okay, so let's go ahead and find the potential energy for this force. And this is just going to be given by some u, I'll call this of x, and this we know is dx dot f. And again, the gory details of this get a bit complicated, and I'm sure that at some point I'll go into much greater depth about changing coordinate systems, but this particular case, since the only component is in the r hat direction, I just get something like this, just the integral over r of f of r, which in our case is minus dr alpha over r squared, which when we take this integral, I get plus alpha over r, and I'll call this minus u naught. And so putting all this together, this is only going to depend on r. This is going to be minus alpha over r plus, again, some constant that we can fix later. And this is our gravitational potential energy. Assuming that this alpha doesn't depend on any position, which we know that it doesn't from our derivation using angular momentum and Kepler's laws. Okay, so why is this all important? This is all important because, again, remember, work, going back to this statement up here, work only depends on the endpoints. So if I can write my force in this way, the work is only going to depend on the endpoints of our path. And in this particular case, we give the force the name of a conservative force. basically coming from the idea that it conserves energy. But this is, so we saw a case, namely friction, where the work did depend on the path. It didn't only depend on the endpoints of the path, but it depended on the exact path we took. So if we took different paths, we got a different result for the work done. So now we can see that all that's saying is that I can't write friction this way. I can't write friction as a vector derivative like this. Okay. So then, this is great for potential energy. But what about kinetic energy? We should still talk about kinetic energy, and specifically talk about it in 3 dimensions. Well, this actually turns out to be much simpler, much more straightforward to do. And we're going to do it in a very similar way as what we did for the one-dimensional case, where we can recall just from Newton's second law that as long as my mass doesn't change with time, I can write the force this way. Which means that when I look at this integral dot f, I can rewrite this as m dx dot a, but I know that the acceleration is the time derivative of velocity. So just writing that in dot dv dt. Okay, so now we pull a bit of a trick, and it's the same trick that we pulled with the one-dimensional case, where if I have something like this, I can treat all of these little d whatevers as independent objects. They're called differentials. And so all I'm going to do is I'm going to swap this dt over to here. So I'm going to say that this is equal to dx dt dot dv. But dx dt is just the velocity. So this is v dot dv. Okay, so now I can rewrite this integral in this nifty way. And I'll just go ahead and write out all the components. dvx vx plus dvy vy plus dvz bz. Which again, these are fairly straightforward integrals to do. And I get 1/2 m times vx squared plus vy squared plus vz squared. And I'll say minus some constant, which I'll call e. But again, this vx plus vy plus vz all squared is just the magnitude of the velocity vector. So I can write this as 1/2 m magnitude v squared minus e. But remember that this very first integral here was also equal to minus u of x. So now, and I'll give this first thing here the name of T of v. This is the kinetic energy. So rewriting this a bit, I have that T minus E is equal to minus U x, which I can then just rearrange everything, and I get something like U plus T equals E, which of course is just our equation for the total energy, where the right-hand side is a constant, which tells us that the left-hand side must also be a constant. Okay, so now I'm going to take a quick break, again, see if there are any questions that people may have again, sort of let people digest all this stuff. And then I'm going to start getting into some of the very useful results and also some of the very deep results that we can find just by using this. So hopefully if you've stuck around this long, you'll start to see a bit of good payoff for all of this work that we've done. Again, no pun intended. Let people think about all this for a bit. Yeah, and I'm hoping that this is somewhat interesting. I mean, the math gets a little bit, mathy, but hopefully, like I said, this'll all pay off. So I'm not seeing anything, so maybe let's just go ahead and see the interesting stuff, see the payoff. Okay, so let's go ahead and think of a force, specifically a force. Okay, here's a question. So I called E some constant. Does that mean it's arbitrary? To an extent, yeah. And that we can see in the fact that when we find these functions for the potential energy, it's only really defined up to some constant u, or u naught. So I can always shift this number that I call the total energy by some amount, and that's actually used quite often to make life easier on us. So in this particular case, we might say that at r going to infinity, right, I might fix u naught to be 0, so that as r goes to infinity, u goes to 0. And that oftentimes makes life a lot easier. But so yes, this E to some extent is just completely arbitrary, because I can fix these integration constants however I want. Good question. Okay, so let's look at a different example, and this is actually an example which comes up in electromagnetism. But so using all of this formalism, we can start to prove some general things, where we're not necessarily looking at a specific system, but a sort of class of systems. So one example might be if I can write my force, which I'll say can depend on x, y, and z, and it could also depend on t. Let's say I can write this as a cross product. A cross product between the velocity vector times, I'll call it some b. This is some vector, some arbitrary vector. It doesn't really matter what it is at this point. But so if I have some, if my force is written as a cross product between the velocity and some vector, or some vector field in this particular case, what happens with the potential energy? Well, let's write this in our nice compact index notation, so that I can say Fi is equal to epsilon ijk v j bk, where if you're a bit fuzzy on your index notation, all this is saying these are the components of f. So so my Fi is going to be one of fx, fy, fz. And on the right-hand side here, if I repeat an index, that means I'm summing. So I can write this as sum over j and k, epsilon I j k, v j bk, where this epsilon, if things are in the standard order, so 1, 2, 3, where 1 could be x, y, z. We might say this is 1. And if I flip two indices, this gives me -1. And if I repeat any two indices, say this case, I get 0. So lightning review, this is just a bit more convenient definition of our cross product. So I did this in an older stream. If this is a bit fuzzy, that's okay. But okay, so this in this case, our potential energy again could look like this, and is just given by dx dot f, which is going to be equal to minus integral. Can write this in a couple of ways. Dot v dot cross b, or I could write this as minus epsilon I j k integral dx I v j b k. Okay, so now let's use our trick of using this chain rule. So instead of, actually I'll just look at the components. Instead of using dxi, how about I use something instead like this? Just essentially multiply by a fancy form of 1, where I multiply by dt over dt, where t is time. So in this case, I get the velocity in a particular direction, dt. And so rewriting this in this way, I get something like minus integral dt v dot f, which in this case is going to give me something like dt v dot v cross b, or in index notation, minus epsilon I j k integral dt v I v j b k. But wait, we know that when we take a cross product, the resulting vector is going to be perpendicular to both v and b. And when I take a dot product, this only picks out the parallel piece. So I'm picking out the piece of v cross b which is parallel to v, but v cross b by definition is perpendicular to v. So this automatically gives me 0. It doesn't matter what b is, it doesn't matter what this vector is, what it looks like, as long as I can write my force as a cross product between the velocity and this vector. This automatically means that my potential energy is always 0. And all this tells me is that a force like this, does no work. But we shouldn't really be surprised about this, because we know that the force always acts perpendicular to the velocity. So no matter where we are, it only depends on the velocity, and the force acts perpendicular to that velocity. But to do work, we have to transfer some energy to the into kinetic energy. So we have to either speed up or slow down the object. But if the force is always acting perpendicular to the velocity, that's never going to happen. We're never going to speed it up or slow it down. We're only going to change its direction. And so it makes sense that this does no work. And actually this is, again, a little bit sloppy. This should just be some constant, which I'll call u naught. But we can fix u naught to be 0. Like I said, for our convenience, I'll call it 0. So this again is a very general result, right? We never chose a form for this vector b. We just know that if it's perpendicular, or if the force is perpendicular to velocity, we have to get 0, or 0 work done. So that's a very cool result. And like I said, this comes up in E&M. This ends up being the force on a charged particle in a magnetic field. So we find that magnetic fields never do work on charged particles. Now I'm going to do a couple more examples before wrapping up. And these are actually going to hint to us at one of the most fundamental things in modern physics. Something used all the time in theoretical physics, in particle physics, all this stuff. We're going to just get a bit of a taste of it. We're not going to prove it, but we're going to see it in action, essentially. So if we think back to our gravitational field, so I have something like this, and I have some particle out here, and this is going to be described by some position vector, which I'll call x. Or how about instead, I call it, so in these spherical coordinates, I can say that my x vector is r times r hat. It's only in this radial direction. Okay, so now let's say that instead of writing specifically this gravitational force, let's just say that F, my force is some F only of this position. Really, I should write this as is some F of r hat. So it only points in the direction perpendicular, or not perpendicular, parallel, sorry, to the position vector. Well, in this case, as we saw before, I can write this as some du dr r hat. In which case, when I look at u equals integral dx dot f, this just ends up being some function of r. Right, because, essentially I only get something in the r direction. Or I suppose we can see it another way by going in reverse. Right, so since when I act with the vector derivative on u, I only get something like du dr r hat. This tells me that u is only a function of r, because in principle this vector derivative has derivatives of the other coordinates living in it, but since I'm only considering derivatives with respect to r in the r hat direction, that tells me that u is only a function of r. Okay, so in this particular case, my force is only in the radial direction. So the interesting thing happens when we look at what happens to the angular momentum. Specifically, how the angular momentum changes with time. So to look at that, we want the change in angular momentum with respect to time, which we find d by dt are, or I guess in this case this is x cross p, which I can then use my product rule to get v cross mv plus x cross dp dt. This gives me 0 because v is obviously parallel to itself and has no perpendicular component, So this gives me something like x cross f. Now when I write this out, this gives me something like r f of r hat cross r hat. Because x points in the r hat direction, f points in the r hat direction, which gives me 0. So in this particular case, when I can write my potential energy as only a function of r, that automatically means that angular momentum is a constant. L equals constant. In other words, angular momentum has to be conserved. So I'm going to rephrase this a little bit differently. So in our function of energy, no angles ever showed up. Only the radius showed up, the distance we are from the center. That's all that showed up. So if no angles ever show up in this function, that means that it does not depend on how I rotate the system. So if I rotate the system a bit, it'll all look the same. In other words, I have a symmetry of rotations. When I rotate the system, nothing changes. So in those words, I'll write this down because this is very important. When my energy is symmetric under rotations, that automatically means that angular momentum is conserved. So two things that seem like they should have absolutely nothing to do with each other, right? The symmetries of the system and the conservation laws that this system obeys. Okay, let's look at another example of this, a bit more straightforward, where instead of looking at it in spherical coordinates, let's say that our potential energy is only a function of the y and z coordinates, so it doesn't depend on x. Well, in this case, when I take my vector derivative of u, I only get something in the y and z directions, right? I only get du dy y hat minus du dz z hat. Okay, but I know that my force is the time derivative of momentum. So in this particular case, this automatically tells me that the momentum in the x direction never changes. And so px is again a constant. But now we can again phrase this in terms of symmetry. So if I have a system that doesn't depend on where I am in the x direction, like this means that I can take everything and I can shift it. So maybe I have some particle here, where this is the x direction and this is the y direction. I can shift it in the x direction, and nothing's going to change because there's no dependence on x here. So, in other words, I have a symmetry of shifts, or, as you'll more commonly hear it, translational symmetry. So again, we see that when U has a translational symmetry, this automatically tells me that momentum is conserved. Specifically, linear momentum is conserved. So this might start to hint at something very, very deep, which one can actually prove this, is that symmetries of U, well, and T also has to have them, directly correspond to conservation laws. Now, this is absolutely mind-blowing, in my opinion, because these are two things that should have absolutely nothing to do with each other, right? The thing on the left is something just completely mathematical, right? It's a mathematical thing that my equations satisfy, but on the right-hand side is a very physical consequence, right? Momentum always has to be conserved in any physical process. And so the fact that this appears is something very, very deep and very, very ingrained in physics. And like I said, it's used all the time in modern theoretical physics. And it goes far beyond these symmetries that we talked about, like these physical rotational symmetries. But we're going to need a little bit more machinery to actually prove this in general. But so hopefully this is as exciting to you as it is to me. But I think that that's sort of the note that I want to end this stream on. So if you have any questions, feel free to let me know. I'll hang around for a few more minutes. If not, then I hope everyone has, whatever you celebrate, has or had a good holiday season, and that everyone's staying safe and all that good stuff. Yeah, and yes, capital T is kinetic energy. Yes. Yeah. Actually, time translational symmetry also corresponds to a conservation law as well. So you could talk about time in this, but in this particular case, capital T is kinetic energy. Obviously, because T stands for kinetic energy. Yeah, thank you for showing up. Good to have you. Excellent. Well, not seeing anything else show up. So I hope everyone's doing well, and thank you everyone for showing up. I think I'm gonna log off now. So I'll see you all next time.